Okay, so we are on to lesson 2 for today. We're almost done week 1, which is awesome. And so I'm going to look at misleading graphs today. So the media are major users of data. So you'll often see like our product works here. I think of like the TikTok video, like the more you F around, the more you find out kind of thing. So that kind of graph. So we use a lot of data and addressing issues and presenting points of view. The media relies on information based on data. People love numbers, right? Especially with, and I know it's probably overheard, and I'm personally also tired of hearing about it, but like COVID vaccines, right? If somebody were to say there's like 15% chance of success, there's no way we would have, right? And so people really love those numbers. There's, 1 in 4 or percentages or whatnot. So one of the main purposes of the media is to try to inform the general public about world events in as an objective matter as possible. So, however, the media may sometimes provide misleading or false interpretation to sway the public. So you'll often get things like, 99% success rate, for example. So that's going to make you want to buy their product when in reality, maybe it's like 50% or 60%. So they're always going to kind of mislead you to sell their products or to sway your ideas. So an important reason to study statistics is to understand how information is represented and misrepresented. So I know as an academic brain that I am, I don't always believe everything on there. I'm a little skeptical because it is media, right? So we've got a warm up. So Democrats say that they have won 60% of recent elections. However, Republicans say that they have won 62.5% of the most recent elections. So what's going on? Who do you think is lying? So if you were to look at this, you've got Democrats that are saying 60, Republicans that are saying 62.5. The numbers don't add up. That doesn't add up to 100%, right? So how does that make sense? Okay, so let's examine the real stats. Okay, so you have Obama in 2008, which was a Democrat. So there's one. You've got Clinton in 96, that was a Democrat. You've got Clinton in 92, that was a Democrat. And that's it. So the Democrats are saying 60% they've won the elections, when in reality, out of 1, 2, 3, 4, 5, 6, 7, 8, out of 8 election years, only 3 are won by Democrats. So if we were to look at that, excuse me, I'm dropping things over here. So 3 out of 8 for the Democrats. So if you throw that into the calculator, I bet you it's not 60%. So it's 37.8. So we'll round it up to 38%. Okay. And then Republicans are 1, 2, 3, 4, 5. So 5 over 8, which gives us 5 divided by 8 times 100. So 62.5. Wow, 62.5%. So the Democrats are lying. Democrats. Okay. So that goes to show you an example real quick just of misleading data. So it's important to look at those numbers and to really look at the facts instead of hearsay and, I'm the best, I won 60% of the time, when in reality they won 68. So I'm going to clear this. Other common ways data can be misrepresented is data not displayed properly. So truncated y-axis, area principle violated, missing axis labels, improper scale. So that's just all on your graphs. Sometimes they are done not properly. So obviously they did not take my course. So sample size is too small. So you can't say like 60% of the world or the population eats salmon, right? And you did your sample size as 100 people. That's 100 people out of 7 billion, right? It's too small of a sample. It doesn't work. Insufficient information. So maybe they ask the question like, how many of you eat fish? That has nothing to do with salmon. It's too wide. And then the sample is not representative of the population. Okay, so we're going to look at data not displayed properly. So when you purchase a new vehicle, its value drops dramatically the moment it is driven off the car dealer's lot, and then continues to drop every year thereafter. So a graph is used to show this change in value over time. It is possible to communicate different messages using the same data by changing the vertical scale. Okay, so if you look at the first one, you've got the value of the car and you've got years. So this graph shows the car's value go from 9,000 after 2 years to 1,000 after 10 years. If you look at graph B, this graph also shows the car's value go from 9,000 after 2 years to 1,000 after 10 years. So you've got a bigger scale going here, which would be a little bit more accurate. So look quickly at each graph. What impression does graph A give you about the change in value of car compared to B? So the value of the car in graph A seems to be decreasing, but at a much slower rate than in graph B. Okay, so your slope or your rate of change is a lot slower looking because of the scale than in graph B. So once you look more carefully at both graphs, how does your impression change? What information changed your first impression about the graphs? So the change in the value of the car is actually the same when you look at it. However, your impression likely changed. So they're both the exact same graph, just a different scale. It's just looking at the two, your impression would have been different about the value of the car. When you looked at the scale provided for the two graphs. So scales that go up by small differences exaggerate trends in the data. Okay. So graph A was very exaggerated just because its scale was very small. Okay, so I'm going to clear that and we can move on to example 2. So how did Fox News misrepresent this data? Okay, so we're going to take a look at that. Take a look at it. So this is an example of truncated y-axis. I'm going to clear that. So it looks like the percentage changed a lot from now to January 1st, 2013. But examining closely, you can see that the minimum point of the vertical axis, so this guy, you can see that the minimum point of the vertical axis is 34 instead of 0. So your scale is, what's the word I would use? Like they messed around with the scale to make it seem like a bigger jump, when in reality, it's only 4.6%. Okay, so it makes it seem like this dramatic change. So they messed around with it to show this dramatic change, and to exaggerate the percentage, when in reality, it's not that much. Okay, so this is what it should actually look like. So you can see here, this looks dramatic, that looks insane. Whereas this is not that big of a deal. Okay. So example 3 is the following graph shows the number of people on board the Titanic for each class. Okay, so we've got this. So although the lengths of the ships are accurate, our eyes respond to the area of the pictures. There are about 3 times as many crew members on the ship as first class. But the picture of the ship for crew members has an area of about 9 times larger. So this guy should be 3. Okay, so our crew is 3 times larger than our first, but by looking at the scale, this boat looks huge. So it's showing as 9 times larger than the first class. And so it gives us this perception that there were more people. The area principle says that the area occupied by a part of the graph should correspond to the magnitude of the value. So this guy should really be at a scale of ×3, not ×9, to give you this impression that there are a lot more people. Okay, so scale is very important when we're looking at graphs. So I'm gonna clear this. I feel like it's almost common sense, right? When you're doing your work, I feel like it's second nature to make sure that your scale is proper. You're starting at 0, you're going up by certain amounts that are accurate. Your scale is going to be perfect. Your ship's not going to be 9 times bigger than it should be, and etc. So we've also got the problem of sample size is too small. So a manager wants to know if a new aptitude test accurately predicts employee productivity. So the manager has all 30 current employees write the test and then compares their score to their productivity as measured in the most recent performance reviews. The data is ordered alphabetically by employee surname. In order to simplify the calculations, the manager selects a systematic sample using every 7th employee. Okay, so this is that example of a small size sample where instead of using all 30 of his employees, he's using, a few just to make his life easier. Based on this sample, the manager concludes that the company should hire only applicants who do well on the aptitude test. Determine whether the manager's analysis is valid. Okay. So based on the linear regression of the systematic samples, what would you conclude? Okay. So, I didn't mean to do that. There is a strong positive correlation between test score and productivity. Therefore, the aptitude test is a great indicator of employee productivity. So if you're looking at this guy, it's saying if their test scores are great, then they're super productive. But he only looked at 4 instead of 30. So I'm going to clear this and we're going to look at what it actually looks like. Okay, so based on the linear regression of the raw data, do you think the sample is a good representation of the population? So you're looking at this, there's no correlation, right? So there's really no link between somebody's productivity as opposed to their test score. And that is what happens when you only use 3 or 4 out of 30. Test scores, and productivity. Therefore, the aptitude test is not a good prediction. Okay, so I'm going to clear this guy. We're going to look at insufficient information. So what does this graph tell you about the ability of drivers as they age? Okay, so this guy is telling us that as you get older, they're not better, or there's fewer crashes, sorry. So this graph indicates that drivers get better with age because they are involved in fewer fatal crashes. Okay, so we're looking at that. I'm clearing it. I'm going to try to go as quick as I can. It's already 12 or 10, so I want to get this out to you guys. However, if you look at this, the younger ages and the older ages are more likely to have fatal crashes. So this doesn't even tell us how many people are in it, or there are only, you know, what, 9, and this one is in millions. Okay, so this guy, this graph indicates that drivers are at the highest risk of a fatal crash when they are older than 75 years old. The previous graph was misleading because it didn't take into account how many miles each age group drives. Okay. So this is per 100 million miles driven. So obviously if you drive more, you're more likely to have crashes. Okay. So sample is not representative of the population. So when reading statistics, look carefully for an indicator of how the sample was chosen. Often companies will carefully select a sample so that they can inflate their results. So for example, that would be like somebody selling vapes, for example, and doing their samples where most of them don't vape. So that would be misleading because it's looking at people who don't vape and whatnot. Okay, so I'm clearing this. I'm just gonna make sure we got everything for this lesson. Yeah. Okay, so you're gonna do the independent work. Yeah, so hopefully you guys have enough information and that you understand everything. If you have any questions, let me know. If you feel that these videos are better than the ones I've been posting with the other teacher, please feel free to let me know, and I will for sure just keep making these. Hopefully my avatar looks good enough. don't look fantastic at 9 in the morning, and she looks a lot better. So yeah, good luck.